Well, hello everyone, and welcome back to Adrian's Digital Basement. This is part 2 in the TRS-80 Model II video series. I don't know how many parts there are going to be. To be honest, this machine may never work again. I am not sure about that. But if you haven't seen part 1, I recommend you watch that first because, as usual, this is a continuation from that first part. In part 1, I tore this computer down all the way to the chassis because it really needed some extreme cleaning due to the fact that it was filled with rust, dead bugs, and leaves. Now that it's taken apart, I need to start going through all the various components one by one and checking to see that they're going to be okay to try to operate and eventually get everything together into a state where I can power this thing on and see if it even works at all. So without further ado, let's get right to it. Let's start off talking about fasteners. These are screws that were inside the TRS-80 Model II. And what I did is, because these were very rusty, is I put them inside vinegar and I let them soak for about a week. That pretty much took off all the rust. But what that leaves you with is a screw that no longer has a coating. Like if it had a zinc coating or whatever, it's gone and it will just quickly re-rust again. And I sprayed them with several coats of this rust reformer, which is a rust converter from Rust-Oleum. I find that this works quite well because it actually does a decent job coating these screws, but it's not too thick, so the fasteners will still work properly inside of whatever they were originally screwed into, and they're no longer rusty. I will definitely need to take a second pass at applying that rust reformer to things. Because here's an example. This is that back plate that was on the back of the case that had the ports. And I did give this a little bit of a scrubbing to get all the bug debris and stuff off here. But the fasteners there are very rusty. But take a look at the other side here. The back is much, much worse. What I'm probably going to do, and this will take obviously quite a bit of time, is I need to take this thing apart totally, like get these cables off, which I think the cables are going to be fine, especially with a little Deoxit in here. Take these 3 cables off, take the fuse holder off, and then use some navel jelly, which is like a pink color paste that will eat away this rust. And then depending on how it looks after that process, hit it with this rust reformer spray paint. But I might also take a wire brush and scrape away some of this rust first. I'm not very good at this type of work. I don't have like one of those bench mounted wheels, you know, for cleaning stuff like this with the bristles on there. So all I have is these little attachments to go in my drill. I know this is not going to look perfect when I'm done, especially because when I spray paint it with this rust reformer, it will take away this writing here where it says disk expansion and stuff like that. But you know, to be honest, I'm not too upset about that. It's kind of obvious what these ports are anyways. Not to mention I could make some labels with my label maker if I really, really needed to. But I just know that I can't leave this like that inside the computer because that will not be good over time. Now you see here the front panel. Now I gave this stuff a thorough washing and a little bit of a scrubbing, but unfortunately it's still pretty dirty. The paint is very oxidized. There's a lot of buildup on here, but it is paint, and that's a good thing because paint, it's like something you can actually treat. You can use, like I have a lot of products for taking care of your car, for instance, like a clay bar. So I may try a little bit of the clay bar, like especially on the bottom of the computer here, that'd be a good test spot. Try the clay bar, see if that takes off a lot of this grit and brings back a little bit of the shine to this paint. But at least the dead bugs are gone. It's just, it left the paint pretty ugly looking. But yeah, on the inside of the computer here, there are no more dead bugs, no more dead spiders. Okay, there's a little bit here or there of stuff, but you know, it doesn't need to be perfect. It's the inside of the computer. I'm gonna leave trying to clean up the cosmetics of this computer, except for maybe attacking this rust plate first. I'm gonna leave the rest for after I know that the computer completely works, because I don't wanna go through all the effort of cleaning up the cosmetics to find that there are some massive and unrepairable problems with the machine that will prevent it from ever working. Of the parts you see on the bench, the most important things that really need to work are the power supply and the analog board for the CRT. The CRT itself, it'd be nice to know if this can work, and I will get to that. But it's not like it's a completely unique part. I think potentially I could take one out of one of my monochrome monitors and make that thing work again. And as far as the disk drive goes, I need to figure out a way to test that, which I may leave to the next video. But I think I mentioned in the first video that I actually have a spare one of these, the exact same Shugart 800 drive here, that should work in the TRS-80 Model II if this one is too far gone to work, like it has bearing problems or whatever. Now, as for these boards, which are the digital boards for the Model II, and there are 4 of them, I stacked them up over here next to the CRT because I had washed them and I needed them to dry. Of course, those plug into this backplane here, and I'm not too concerned about this not working. I'm sure with some Deoxit, there won't be any issues. I don't see any massive green corrosion on here. It just needs to be cleaned up. This metal part here, yeah, could use a little help. So I'm holding the mounting bracket for both the CRT analog board and the power supply. And I'm gonna first try to work on the CRT board because I have an idea of a way to test the CRT board outside of the system, so I don't rely on the power supply here or any of those digital boards to test to make sure that the CRT is working. So bringing this into shot here, I'll just move this stuff out of the way. I have already used the compressed air outside to blow as much of the dead bugs and dirt and stuff off of here as possible. Down here on this board, there was so much debris, so many dead bugs, it was just horrible, and I'm sure there's still gonna be a little bit left in here. Now, unfortunately, you can probably just see it right there, there's a good amount of rust on this bottom part of the bracket. So I'm gonna need to remove the power supply and the CRT board off of this bracket and then give it the same treatment I give to that backboard where the ports were. At least trying to sand this down a little bit because I think the paint is flaking off a bit, and then applying the navel jelly and putting the rust converter and whatnot on it. It's not in terrible condition. It seems like the corrosion is isolated to the bottom where it was screwed into the chassis. Let's look at the bottom here. Even that doesn't look terrible. Definitely the paint, sorry, it's a little hard here. The paint's flaking off here though. So this part, I'll probably have to sand this down to try to get this paint off, or powder coating or whatever it is, and then apply that rust converter, well, after doing the navel jelly. Now, my one concern about the operation of this machine, and one of the reasons why I keep saying, it may not work, is that because something like the Flyback Transformer, which is right here, that is not waterproof, especially old ones like this. Water could easily get in there and have damaged it, like cause corrosion on the windings or whatever. And because it's rated to run at about 12,000 volts, this particular CRT board here, any kind of issues with the isolation or the insulation on those windings can really wreak havoc. Now, maybe I can find a replacement board that would work in place of this. I'd need the deflection yoke as well, most likely, because the inputs to this, I have peeked at the service manual, and they are just normal 15.7 kilohertz, which is, NTSC basically, 60 hertz, 640 by 200 non-interlaced, typical CGA type resolution. And because of that, there we go, this is free. That's not too uncommon. I'm pretty sure that like the other TRS-80 Model 4 uses a very similar type board, and any monochrome monitor, to be honest, that would be for like an Apple II, a composite type monitor, might be able to be adapted to work. The video board in this computer just gives out TTL, horizontal vertical sync, and a video signal, a monochrome video signal. It's just 3 wires. So that's why, like, if worse comes to worse, I could try to source something to replace this. I'm not positive. If I move this bracket thing here out of the way, yeah, so if water had gotten into here and caused a lot of leakage, then it may never work. This transformer right here is probably fine. There's definitely evidence that water has been along the bottom edge of the CRT board. Because this runs at 12,000 volts, you need the insulation to be in good shape and working properly. I mean, I've had monitors where the flyback died with no water ingress just from breakdown from the high voltage over the years. That is a common failure point. And in case anyone's wondering, these are not universal. You cannot just take a flyback from another monitor and stick it on here. All of the windings, there's various windings, are very custom usually to this board because the flyback doesn't just generate 12,000 volts for the CRT high voltage. It's also part of the horizontal deflection circuit. It is handling all the boost voltages and other things. So it's a very integral part to the monitor. So if it's bad, this whole board is going to be toast. All right, so let's get this Aztec power supply off of here. Let's see, this is a pretty cool looking power supply. I haven't really looked too much at it, but it's got a Aztec control module here. And remember, this machine is from 1979, and switching power supplies at that point were not super common. Apple II had one, but the TRS-80 Model I did not have one. Let me try and think of what else there was out at the time. The Commodore PET, obviously, that just had a giant transformer and linear regulator, so it was not switching. It just is all pretty new stuff at the time. I'm noticing on this power supply, it's got a little lead here to switch between 115 volts and 230. So if you have one of these, you want to adapt the voltage, you can do so. But keep in mind that the floppy drive, the 8-inch drive, it takes mains voltage directly into it. So the US drive isn't going to work properly on the wrong voltage, but even with a voltage converter, it's going to need the frequency adjusted as well because it relies on the frequency to get the disk speed right. This right here is most likely part of the feedback circuit, this transformer, and that connects the low side, which is this stuff right here, to the high side, which is over here. This is the high voltage area. So I think this power supply is going to need to operate in a relatively narrow range of load. So you can't just run it with no load, and too much load, well, it would probably trip the overpower or overcurrent protection. But not enough load could damage the power supply. It may be able to detect that the no load situation is happening and just shut off. But typically when you have these transformer-based feedback circuits, modern power supplies use optocouplers. Things can get a little crazy if you plug them in with no load or you have some of it loaded and other parts not. So it's a bit of a mystery there. There are these bead diodes right here, and these are very susceptible to damage from moisture. But the fact is, there are 4 of them. Oh, there's actually 5. So I don't know if those are used for, like, if this is rectification over here. It's also this thing right here plugged in to the heatsink. That could be also a diode. Yeah, I'm not sure the topology of this thing. But either way, those are pretty bad when it comes to corrosion. And they do seem to be intact, but I don't know if they work properly. I'll be able to test that. Anyhow, it was not my intent to focus on this power supply. I wanted to focus on the analog board, but I do want to get this thing ready for sanding and ready for the navel jelly. And it looks like these fasteners here for the heatsink, I also need to throw them into the vinegar because they are rusty. It's sort of one of the issues when something is in a condition like this machine, in such rough condition, it really means that troubleshooting is that much harder because I can't just fire this thing up and expect it to work when you have these types of things like these diodes which can die. And if there's some problem with the power supply, it could easily just kill the rest of the computer. So I have to be so careful about what to do with this thing. And of course, then all the rust and the corrosion on everything else, it adds so much more to it than troubleshooting some digital circuits, which is really what I'm good at. I'm not nearly as good at fixing power supply boards and analog stuff like that. So I have some screws in this little container here ready for vinegar, and a few of them were off the CRT, or off the power supply rather, and I needed to take care of the rust. So I decided to go and grab this board and pull off the various cables off here, and it is in such rough shape. I mean, just take a look at that. Look at that rust. That is bad. I don't think it's too far gone. It is still fixable, but there's just so much rust. I'm really gonna have to go all over this thing with that wire bristle brush thing and try to flake off this paint, put the rust converter stuff on it to get rid of the rust, you know, and do that whole process to it. Just the bench has like rust dust everywhere. Now, this was the serial port cable that was on there. The other cables are completely fine. There's no issues with them. These, on the other hand, are not in great shape. I mean, maybe it's fine. Deoxit, again, you know, inside of there with a brush, and who knows. There is also this little board here, which was in that section. This is where the floppy drive connector was. And the back side, which is what I could see, looked okay. But this side, yeah, not so great. So it'll get the same treatment as all of this. Oh, and one of the screws, this one right here, unfortunately, taking it off, the threads came off with it. So that is no longer. Hopefully this thread pitch is pretty standard and I can just find another replacement one. I don't think it's gonna be a problem, but the rest are in here. Oh, and then what I did for all the nuts and washers is I put them inside this little case here, and I wrote disk drive, this is the fuse holder here, serial and parallel, these are all the nuts and the washers. CRT board are these, and the PSU is these, and of course there are some of screws from various ones of these in there. But this is just a good way for me to keep those separated from each other. All right, so we're ready for some basic troubleshooting of this board. I'm not even gonna look at the schematics yet, even though I have those at the ready. I'm gonna use the multimeter on Diode Check first, and I'm just gonna check to see if the semiconductors, the diodes on here, and the transistors and things like that are not shorted. So that is the first thing we want to do. Let's flip this over. Does this have markings? It does. Very nice. So I'm going to go through all of the connections here, and I'm going to check for correct diode drop. That one looks good. And or just make sure things aren't shorted. That is good. That is good. So these are transistors here. Not shorted. Not shorted. I'm going to skip over the L's, which are inductors, and the R's, which are resistors. And I'm just going to check everything that says D or Q. All right, so everything looks fine except for D10. Where I get a short, and I get it both directions, 0 ohms. But let's flip this over. Maybe they replaced that with something else. Oh, they did. So hopefully you can see right there, but D10 is a wire jumper link. So that is not a fault. For something like this that's been off for who knows how long in moisture or whatever, it's a good first test to do that check. And the reason why is because a shorted semiconductor, like for instance, if one of these main drive transistors were bad, it could just destroy all sorts of things on this board when I attempt to power it up. But everything seemed good. So that doesn't mean this thing works. It just means that it at least doesn't have a short across one of the semiconductors. All right, next up I have this, and that's only good for measuring these larger electrolytics, especially with these long leads on here. And you do have to connect them up with the correct polarity. So for instance, this blue cap right here, I'm just gonna hook this on to both sides. Oh, there's a dead bug there. And we get 546 microfarad, and I can see that it's 470 at 16 volts. Now it's reading a little bit high, but that could be because of age, but it also could be because there's stuff in parallel to that. It doesn't look too bad, and the D value, which is 0.67, seems okay as well. If the D value were very high, then I'd be concerned. Like if the number was 3 or 4 or something like that. Next up, we have 100 microfarad, and we're getting 99.2 and a 0.26, so that seems okay. Now we have this big chunky power one in here. It's 2000 at 35 volts. Might be a bit much for my meter to read, actually. It just says OL. I'm going to change the frequency to 100 hertz. See if that works better. There we go. About a little under 2000. 0.15 is the D, which is fine. Next up, 22 microfarad. Okay, we're getting 26 at a D of 0.063, which is quite low, so that one is fine. To be honest, so far the only one I have I'm suspect about is this 470. Let me just measure it again. At I have it at 100 hertz. Okay, at 100 hertz, the D is actually 0.09. The frequency you're measuring the caps at does matter. So keep that in mind. The larger ones are generally better measured at the lower frequency. This board doesn't really have a lot of electrolytics. There's a couple film caps here and there and there. And there's one more electrolytic over here. I am struggling to get this clip on that side, so I'm going to flip this over and connect it on the back side, and the other one fell off. So we'll just connect it on the back side as well. We are getting 25, 26. See what this is supposed to be. 22. All right, so that looks good. So all the electrolytics look fine. So semiconductors are good, electrolytics are fine. We're getting much closer to being ready to test this thing out. I think what I want to do next is I'm going to give this deflection yoke a little bit of an inspection. So what I'm looking for in here is any kind of corrosion, like obvious corrosion, like green basically. And that might come from the insulation breaking down and moisture getting in here over time. I'm not seeing it though. This all looks really shiny and kind of a nice copper color. It's a little black and sooty right there, but that is the top. So all the heat and soot and stuff will go to the top, so it is worse there. But everything looks, yeah, nice, really nice. So now I'm just checking to make sure that these connections are still in place, and they are. And on this one, same thing, there's some Celastic holding it on. There are fine little wires that run from here, soldered on, into the coil itself. So I want to make sure that those aren't broken. So there's one of them right there. A little bit of glue holding it down, but that looks fine. So the high voltage anode cap here, I talked about this in the first one. I looked in the manual to figure out what's going on here exactly. I think what's happening here is this is the high voltage right here that comes out of the flyback. Inside here is a diode or a couple diodes, and that is like the rectification, so to speak, because this will have AC coming out of here, and the CRT is a big capacitor. It needs DC. So there's some diodes inside of here, high voltage ones, and I think this does come apart, although I'm not gonna pull that apart, because it mentioned in the manual, if you wanna leave this connected, you can disconnect this. All right, then I looked at this second cable here, this one that comes out of the high voltage cap, goes back to the board through this. Well, it turns out that it connects right here to ground. So why would the CRT high voltage cap have a ground on it? Well, it turns out that inside here is like a 240 meg ohm resistor. Basically, it's a bleed resistor. So it drains the high voltage once you turn the CRT off. Maybe it also applies a little bit of load to the flyback, but I don't think that's the reason. I really think this is just simply a bleed resistor to reduce the high voltage on this thing. So when you turn it off, it actually does that bleeding for you over time. Now that's for the flyback transformer itself. There's really no way for me to inspect this. This black part here is like rubber, and it looks like some of it has come away right here. And unfortunately, the windings are sort of exposed. I don't see any green corrosion there, but that's very worrisome right there. I hope that's not going to be an issue. Now you might have also noticed right here, it says Motorola serial number 93097375. So yes, this board is definitely made by Motorola. I am just closely inspecting right now to see if I see anything that's blown up or obviously burned or damaged, because you never know what you might just see using your eyes, and might be a bad resistor or something like that that I could just replace and avoid turning this thing on when something like that is open or has the wrong value or something. So everything on the top side looks fine. Really not noticing any issues. So now I'm just going to do the same check on the bottom here. I'm just looking for obviously bad solder joints on here, and so far things look okay. All right, I have the CRT on the bench here, and I have plugged the, I think it's gonna work, analog board into it. I put a mouse pad under the analog board so it doesn't short out to the chassis. I've also gone ahead and I removed, there was some AC mains wiring still attached, plus the fan on the chassis. I took those out just to make extra space, plus I need to clean anyways. So this connector right here, this is the 12 volt input for the monitor. And looking at the technical manual, here it is, 12 volts in. So this is for the CRT board. That goes to pin 7. It's the purple wire. And I went ahead and I connected these leads here to the purple wire, which is pin 7. And I connected this black lead here to that pin, which is the ground connection on the 12 volt input. And then for getting a signal into this, I've come up with this. So this was the original connection, which has vertical, horizontal, and the video signal along with the ground. This is what plugged into the video driver board on the TRS-80 Model II. I've gone ahead and I've connected that up to a 9-pin connector here. I've soldered the wires to the green, the ground, and the horizontal and the vertical. And this is for connecting to a CGA card on a PC. And I was easily able to figure out which pin is which because it says here P1, that's connector 1-8, and there's the connector right down there. The 8th pin is video in, and the board actually is labeled 1 through 10. So that is an orange wire. Now over on this connector, there's no orange wire, but that's because it goes to this knob here, which is obviously the contrast. This one here will be for brightness, and this monitor actually is capable of displaying shades of gray, but it's accepting a TTL input, so this potentiometer just adjusts the overall screen brightness. So the orange wire changes over to the yellow wire, which loops back around to this connector, and there it is, and I have that connected to the white wire, which is going right here to the green on this DB9, and then I have black for ground, and I have the horizontal and vertical connected all correctly. I also have the high voltage anode connected right here. I have the deflection yoke installed. I have the connector on the back of the CRT. And of course, I connected up this black wire here. I know it's a little hard to see, but that is the ground lead for this thing. So I think this thing is ready to go. I'm going to be testing with this board on a PC right here. This supports monochrome and CGA. We have to run CGA, even though this is a monochrome monitor, specifically because this monitor runs at 15.7 kilohertz, which is what CGA outputs, not monochrome. So there's a switch here that says MDA or CGA. We'll make sure it's in the CGA setting, which is down towards here. And I guess I gotta hook this all up and we're ready for testing. I'll position the camera here in case anything explodes when I turn this on, because it may. In fact, I'll probably unplug this from the CGA connection first. I'm just gonna give this board a quick power up with no input signal. Just in case something does blow, I don't want to feed back into my computer here. I mean, it's the test bench, it's not the end of the world, but I'd rather not destroy this thing. Up here on the power supply, let's turn this on, and first we're gonna reduce the current. I don't know what this thing needs. We'll start at 1 amp and we'll go to 12 volts. And I'm just double checking the connections here. Everything looks good. Nothing is shorted. High voltage is connected. The ground is connected. I guess I'm ready for testing. Here we go. Okay, so we're settled at 157 milliamps, which is fine. There's no input signal on this, and it's almost certain that it's not going to generate high voltage without its input signal, because the horizontal sync signal is what's going to drive the flyback, and that almost certainly is going to generate the high voltage to actually turn this on. So just some of this electronics and the filament we're running at that point. So we'll turn on the computer here because there was no explosion. And I guess, here we go. Okay, so we're still at 160 milliamps, which is too low. Let's turn that off. So I fired up the RGB to HDMI just to make sure that this whole test bench was outputting a correct signal, and it is. That is definitely a CGA signal there. So without that working, of course, we're not going to get anything on this monitor. So that is a good check. Always check to make sure that your test signal is in fact working. I'm just double checking that everything is good on this connector, and it definitely is. Yeah, let's make sure everything is good here. I mean, for sure I need the ground and the horizontal sync, which we do seem to have. Okay. All right, I just double checked everything is connected. I'm going to turn this back on one more time. Yeah, we definitely do not have normal operation of the CRT. Is the filament operating? Yep, the filament is glowing, so I can see that the 159 milliamps on here is probably entirely the filament. All right, it's the next day, and I did some troubleshooting to figure out why the monitor wasn't seemingly doing anything. And if we look over here to the TRS-80 Model II technical reference, over here in section 7 for video monitor, under theory of operation, it talks about the horizontal drive circuit, and what it's looking for are pulses of approximately 27.5 microsecond duration. That's for horizontal, and it wants positive pulses. So it starts at ground and it goes up to 5 volts or thereabouts. Well, it turns out that most CGA cards, including the one I was using last night, which was this one right here, I was connected right to the 9-pin output. And this card here is the compact portable one, and I decided to try to drive the CRT directly off the connector that drives the CRT inside the portable case, thinking that maybe those signals were a little more appropriate for driving a CRT directly. Well, unfortunately, both this card and the other card, which I assume is CGA standard, are giving a pulse of approximately 4.5 microseconds. And you're probably wondering, what is this screen I'm showing here with this oscilloscope waveform? Well, I actually have a National Instruments virtual bench, which is a device that's like an arbitrary waveform generator, 2-channel oscilloscope, logic analyzer. It has a multimeter and a power supply all built into this one device. This was donated to the channel by a lovely viewer here in town, Tyler, and I've had it for quite a while and I actually haven't used it yet, I'm ashamed to say. And I finally realized that this might be able to allow me to test the CRT because of the function generator capability of it. I can generate the exact signal that the monitor needs for the horizontal drive. But on top of that, it's also a 2-channel oscilloscope, which is what you see on screen here, which allows me to easily show this stuff on video versus filming my Rigol scope, which doesn't have video output because I have one of the lower end Rigols that does not have VGA. Now, the Rigol, some people are going to probably say, which is sitting up there on the top, has some software you can run, and over Ethernet or USB also get a representation of all the controls. But I found that software to be unreliable, difficult to use, and really slow. This virtual bench software, on the other hand, is not bad, I have to say. It really isn't bad. The waveform update rate is pretty good. And so I'll probably be using this more in the future. Anyhow, channel 1 here in red, this is the signal actually coming off of the video card. And as you can see right here, that's too short because the documentation is quite specific on the length of the pulse it needs. And looking down here further in the documentation, we can see the schematics for the monitor. And what I did to figure out that the pulse was just not good enough is I started measuring, this is the horizontal drive input. These are the transistors that start to amplify the signal, and then this is the primary horizontal output drive transistor, which ends up creating this waveform here, 130 volts peak to peak, which I think this feeds into the Flyback Transformer. This generates the high voltage and also feeds off somewhere to the yoke. Well, what would happen is when I'd power up the monitor and I'd be checking these waveforms, like this one right here, 6 volts peak to peak, it would show up for a second and then it would collapse. And the same with this output one. So the monitor would never generate any high voltage. Now, I don't know for sure if it's still the flyback that's bad. It could be. But I need to at least get the correct signal into this thing first, just to make sure that it is not a problem with the signaling and to help isolate the particular issue. Now, the funny thing is this board is the Motorola board, as we've talked about. There are 2 boards. There's the Motorola one, this one, and there's also one made by RCA. And the specs for that are further down in this document. In fact, here they are right here. I'll rotate this back so we can read this properly. So here's the RCA input, and take a look at this. The horizontal input is good from 4 to 25. So it's almost like if this were the RCA board, it would actually work off this compact board or potentially right off the CGA port. But the Motorola one is much fussier and needs that specific length signal that it cannot work down to 4 microseconds. There is one other issue though, and it's the vertical as well. I haven't even talked about that, but it's negative going here. And it is the same for this board here, the Motorola board. It needs to be a negative pulse, so it stays at 5 volts all the time and then drops down to negative when there is a vertical sync. And unfortunately, the CGA output connector, the 9-pin here, outputs positive sync pulses. Both of them are positive. So that's not going to work either. But on the other hand, this connector that drives the CRT and the compact portable, it does give the correct negative going pulse for vertical. So this is actually an appropriate signal right here for that. So that's kind of exciting. So over here on the bench, I actually have the waveform generator generating the particular pulse that I need. Let me just switch over the sync. We'll change that and we will measure with the cursors here. So this is the signal that I am generating on the virtual bench. So this is the new horizontal sync signal. So currently the pulse width of the positive pulse is right here, 27.242, so close enough. And if we want to see the actual frequency, it is right here, 15.79 kilohertz. I mean, I wasn't exact with my cursors, but that's going to be close enough that this signal hooked up to this analog board, when it's powered up, if everything is working, should bring the monitor up. It should start generating high voltage. If the flyback has a problem because of damage from the water, it's going to show itself when I power this up. All right, so this cable here, this is coming from the signal generator. I have the ground connected first. On the oscilloscope here, we're looking at the signal coming from the PC that's sitting here. I'm going to unplug what I think is the horizontal drive. There we go. All right, and here on the oscilloscope, we're picking up the signal that's being generated by the virtual bench off of the base right here. It would be this one right here, Q3, the base. Actually, I've moved the probe right to here, so this is the base on the actual horizontal output transistor, which right now we're not going to see anything because the monitor is not powered up. I have left the horizontal sync and also the video signal from this card connected. So there probably will be a picture, but it's going to be all out of sync because obviously the sync pulses for horizontal coming from this have nothing to do with the video signal that comes from this thing. Okay, I think I'm ready to go. I see the ground cable is connected. Everything is good. This could explode, but here we go. Let's hear if we have high voltage. All right, well, good sign on the screen here. I do have the waveform. Oh, look at that, everyone. We have a working monitor. Look at that. Wow, it's actually working. Let me fiddle with these controls a little bit here. The two potentiometers. Okay, they're very scratchy. Now remember, the out of syncness of this is purely because I'm generating the horizontal sync from something other than the video card. How about this one here? There you go, that's the brightness control, obviously. And this other one here is the contrast control. Oh, success! Success! How do I adjust this? How do I adjust this? Ah, there we go. Okay, there we go. So that's the waveform. Let's look at the schematics here. So that is the waveform we're supposed to see going into the base of the drive transistor. And that certainly looks like that. It needed the exact signal that it wanted, and it works. So what I can do is I can adjust the sync rate ever so slightly. Let's see, that should have an effect on the rolling. Now, oh, by the way, I also seem to have the deflection yoke upside down, which is why the picture's rotated 180 degrees. So I am adjusting the frequency here. That should change this. Yep, it is. So here we go. Let's see if I can stop this rolling. Very nice, precise control here. Just trying to get this exactly synchronized to the video card. There we go. There we go. CGA card. Now it will slowly drift over time because of course that sync signal, like I said, is not synchronized to the PC, but it works. It freaking works. Oh, this feels good. This feels good. TRS-80 Model II left for dead, and yet it's actually working. Oh, how cool. All right, I'm going to turn the power off to this monitor, which is drawing about 900 milliamps, by the way, at 12 volts, in case anyone's interested. I'm going to turn this power off and I'm going to flip the deflection yoke around so we can see the picture correctly. All right, I've rotated this around, and it wasn't easy because of the way the wires are all interacting with each other. I'm pretty sure that on the original machine, this was the other way around with the label facing up. I'd have to go check my footage, but that's kind of weird that it seems to need this flip on the PC, and I'm not sure about that. Anyhow, let's turn this back on, and hopefully it doesn't blow up. Okay, we have a good waveform on the horizontal sync. There it is. Yeah, looks fine now. Of course, it's a little out of sync. Let me move this over. Well, other than being rotated, let me just rotate this. There we go. Now you notice it actually has shades of gray, which you wouldn't think possible, right? But that's because the cathode drive circuit in this board actually does support shades, like monochrome shades. But the TRS-80 obviously outputs either on or off, so it's completely monochrome, and CGA would normally be that way as well. But this card I'm using to drive the monitor with, the direct connection that goes to the internal CRT on the compact portable actually takes the CGA colors and converts those to shades, so that the output video signal on here actually is giving this thing correct shades, which is what we're seeing. And I can see it's slightly drifting over. Let's move this over here. Oops. Let's see, 5. Let's try to get this centered. Need to turn this down slightly. Anyhow, it's definitely working. So I'm gonna let this sit a little while and warm up and just see what the picture quality is like. But I gotta say, it actually looks pretty good right now. Not really seeing, oh, it's drifting. It's drifting. Oops. Let's get this back over here. Not sure which way I need to make this to keep it from drifting. I mean, there's not much I can do for the drift. It's gonna slowly drift no matter what I do. Okay, it's going the wrong way now. I can just try to get it as close as possible that it sort of stays centered. Now, I do see some blooming going on here. Let's turn down the brightness a little bit, or that's the contrast. And let's see about this brightness knob. So we're actually starting to see the retrace lines here, so you want to just turn it down just below that and then adjust the contrast appropriately. Well, the CRT's been running for about 25 minutes and still working, no glitches. It actually seems to be a pretty good picture as well. So I'm gonna say that this is a win, and this CRT works absolutely flawlessly. So it really does feel good to at least know that one part of the TRS-80 Model II completely works perfectly. And I guess the next step will be to try to attack that power supply, because if that seems to be working, then I guess after that, it's putting those cards back into that card cage, plugging it all in together to the monitor, and firing it up outside of the chassis, of course, and seeing if we get the diagnostic boot screen that it's supposed to do. Reading the manual there, the technical manual, it talks about what it does when you first power it on, and it should make the screen completely white, and then it does some diagnostics. It's printing a couple errors if there are any issues, and then it tries to boot the floppy disk. The ROM on this machine is interesting the way it works. It's 2K in size, so it's very small. It's just a little bit of a bootstrap. Does the quick diagnostics, the initialization of the system, and then it starts to load the OS off the disk. And as soon as it does that, it bank switches itself out of memory, out of the memory space, that is, of the 68 or the C80. Not the 68,000, the Z80. I keep thinking about the Atari ST. And that gives the entire address space over to RAM and doesn't waste part of it, like the 2K, for just that bootstrap ROM, which won't really be necessary once the system is running. So it should give us some insight into the functionality of the rest of this machine, but that power supply is the big question. Anyhow, yeah, this is part 2. Thank you very much for watching. Huge thanks to all my patrons. Their names are scrolling up the side of the screen. If you want to become a patron, you can do so. There will be a link in the description below. If you like this video, big thumbs up, etc., etc. Also, I want to say thank you to the local viewer who donated this machine to me. I am not sure I thanked him in the first video. And I guess that's going to be it. So stay healthy, stay safe, and I'll see you next time. Bye-bye. Let's turn off the power here. Are we gonna get a spot like we do on the old pet? Nope, it just instantly goes away.